So now that we've discussed the limits of summations, we're actually now equipped with the tools we need to solve another basic problem of calculus, which is the area problem. And integration is what is used to find the area of some region that is bound by a graph. So if I asked you to find the area underneath a particular curve, and I gave you the curve like something, if your function were something linear, something like this, and I said, hey, can you find the area underneath the curve from 0 up until something like 10, for example? And I said, hey, can you find this region right over here, underneath this curve? And you would say, sure, no problem. I know that's a triangle, so I can really just go 1/2 base times height, right? Or if I gave you something like a rectangle, and I said, we've got a constant graph. Can you find the area up until 10? And you'd say, sure, Mr. No problem. I can find this area pretty easily, right? It's just going to be length times my width, right? And that would seem easy enough. What if, however, I gave you something like this? And I said, find the area underneath this curve from 0 to, and suppose this number were 10. I'm just choosing an arbitrary number. And I said, find this area right over here. Well, what would we do? And the answer is integration. But before we can just flat out just say integration, let's take a couple steps back and talk about some of the, no pun intended, building blocks of this. But you won't really get that joke until after I demonstrate this. So we understand what the issue is. We know we can't just use a simple geometric formula here in this case, or can we? What if I wanted to find the area, and let's get rid of this stuff because we get this idea. We know that's easy. What if I asked to find the area underneath this curve, and even though we don't have one formula to fit this particular shape, what if we could break this up into smaller shapes with formulas that we do know, with geometric area formulas that we do know of? And that process of using, in this particular case, rectangles to estimate this area underneath the curve is the process of using something called Riemann sums. And there are two different types. There are left and right Riemann sums. So let's go ahead and actually work with an actual function here instead of just this kind of terrible drawing that I have. So let's actually work with an actual function here and see if we can find the area underneath its curve or estimate it using a Riemann sum. And hopefully this will make a little more sense. So, all right. So let's approximate the area, that should say area, of the region bounded by this particular function, the x-axis, the lines x equals 0, x is equal to 1, using 4 equal intervals, using a right Riemann sum and a left Riemann sum. All right, so first things first, let's go ahead and come up with a table to kind of plot these some key points here. So we see it's a basic quadratic, and if I'm going to go from 0 to 1, I want to go, one of my boundaries is going to be x is equal to 0, and my other boundary is going to be x is equal to 1. If that's the case, let's come up with 4 key points. So if the first point is at 0, the next one would then have to be 1/4. The one after that would then be 1/2, 3/4, and then 1. All right? And what are the y values at those specific points? And you can just use a calculator here if you don't want to do the math, but we can just come up with the following. And 3. All right, so here are our coordinates. Now we're going to go ahead and plot those. And I'm just going to go ahead and show my little table here. Okay, so let's plot those points. So let's actually number these. Obviously, I'm going to scale this a little bit differently because I'm really trying to highlight what's going on here at the beginning of this parabola. So we've got, this is going to be 1, 2, and 3. And you know what? I probably might need some sub intervals just to make this a little bit easier for me. All right. So when x is equal to 0, y is equal to 1. When x is equal to 1/4, y is 1.125. So just a shade above that. At 1/2, we have 1.5. At 3/4, we have 2.125. And at 1, we have 3. So I'm going to use a different color here. but we're going to get something that looks a little bit like this. Okay, and hopefully that didn't confuse you too much, but there's my curve, okay? And I am only concerned with a boundary up until x is equal to 1. So my first boundary is at x is equal to 0, and my second boundary is at x is equal to 1. All right, so now I want to go ahead and try to estimate the area underneath this curve, starting with what we call a right Riemann sum. And what that just basically means is we are going to break this up into 4 rectangles. If it is a right Riemann sum, that means the right corner of that rectangle is at that point. And in drawing my curve, I realized I kind of covered these up, so I'm going to go over them again. So what that means is my right corner of my rectangle is going to hit that next point. So my rectangle in this case, and let me actually zoom in on this just to make this a little bit easier, is going to look something like this. All right, and I'm going to use a different color here. I'm just going to kind of shade this in this way. So there's my first rectangle for my Riemann sum. All right, and now I'm going to continue on and draw the rest of my rectangles. So my right corner of my rectangle is the point that hits the curve, our graph. So we've got this one, and then we've got this one. I went a little bit over for this one, and then finally up here at 1, 3. Okay, so now I'm just gonna kind of lightly shade those in, just so we can see what's going on here a little bit more clearly. So what I have now is a right Riemann sum. This is an estimation of the area underneath this curve. It is not the exact area, obviously, but it is an estimation of the area underneath this curve using right Riemann sums. Now, I know some of you might be thinking, wait, I thought we were trying to find the exact area underneath the curve. We're getting there. We're getting there. But let's just pause and think about how we can leverage what we've done so far and use what we have. Well, you know that the area of a rectangle, so let me zoom out a little bit. We know that the area of a rectangle is simply length times width, or in this case, height times width. So area is equal to height times width. Now, what are those values in the context of this problem here? Well, our height is always going to be a y value, but specifically, it is the output of the function at any given x value. In other words, it's f of some x. F of some x. So given some x value, we have the height at that x value. We have the output of the function at that x value, which is the height. So for example, at 1/4, we have the height of the rectangle. So let me just write this to the side. When x is equal to 1/4, f of 1/4 in this particular case was what? 1.125. And that is the height of that first rectangle, right? So you can see f of x is always going to be our height. Well, what about our width here? Now, we might be tempted to just say our width is just whatever x is, and it makes sense for this first problem. Our width here is indeed 1/4, right? But what about for the next rectangle? Is the width of that rectangle 1/2? No, it's still just 1/4. So how could we notate that? We can just say that the width is always going to be 1/4 in this case, but in general, the width is always how much more you're adding to that previous x value. So what are we adding every single time to our x value to get the next subsequent x value? Well, we're adding 1/4. That is our delta x. In other words, our change in x. Let me write that. Our change in x. We call this our delta x. It's a Greek letter, delta x. It's our change in x. So our x values are changing by 1/4 each time. So that's always going to be our width. Well, now let's go and see if we can come up with the actual area of, well, not the actual, still an estimation, but let's actually calculate what we found here. So we're going to say the following. We're going to say our area is approximately equal to the following. It is our height and our width. So f of 1/4 which we know, times 1/4. And you know what? Let me just actually really make sure we're understanding what we're saying here. This is, again, our height, and this is our width. Okay, plus f of, in this case, 1/2. So at f of 1/2, we had this particular y value, which represents the height of this next rectangle. Okay, f of 1/2 times, what is our delta x? It's still going to be 1/4. And we're going to continue this. So now we've got f of 3/4 times 1/4. And then plus f of 1 times, again, 1/4, right? So we're just repeating all that we just did up here. We're just repeating it for every single one of my rectangles, okay? So we're actually going to evaluate now. So let's see what we found. So we've got 1/4 times, and you know what? I don't want to sit here and multiply everything by 1/4. I notice that I have 1/4 in every single one of my terms that I'm adding up. So let's just factor that outside, and everywhere else, let's just come up with what f of 1/4, f of 1/2, f of 3/4, and so on, what those values are. Well, we found those over here in our table. So I'm just going to jot them down. So we've got 1.125. That was our first height. Then 1.5 plus 2.125, and then 3. And doing some calculating here, we can say that this area, the area underneath this curve, is approximately 1.9375 units squared, since we're talking about an area. So that's what we have approximately, okay? And that's going to be a terrible rectangle, and I didn't think it was going to recognize that. Sorry. Let me go ahead and redo that. All right. So that's our approximate area underneath this curve. That's what we were able to find using a right Riemann sum. Now, ask yourself in this case, does this look like it would be an over or underestimate here? And if you said overestimate, you'd be right. It's an overestimate. Okay. So now that we've tried one of these, you are welcome to now try doing a left Riemann sum on your own. And this time it means that the left corner of your rectangle is hitting the function. Think about what that might look like. And if you're still not sure, let's just do that right now. Okay. So I'm going to take the same scale that I used previously, okay, to do a left Riemann sum. All right. And this time I am going to, well, let me plot my points again. So this was 1/4. And let's see, when 0 gave me 1, 1/4 gave me, let me zoom in on this. 1/2 gave me 1.5. 3/4 gave me 2.125. 1 gave me 3. And again, I'm going to use a different color here. I'm going to try that again. That'll work well enough. Okay. And we've got our boundaries. One boundary was at 1. The other boundary was at 0. And we're going to try to estimate this time using a left Riemann sum. So what would that look like? This time we're saying our upper left corner of our rectangle is hitting the function. That means our left corner is going to be right there at 1. Now for my next rectangle, my left corner is hitting the curve. Left corner is hitting the curve. So again, we're still using rectangles, but now with the left Riemann sum, we're seeing this appears to be an underestimate. And let me just go ahead and just quickly highlight that so we know what we're trying to find. Okay, so you get the idea. All right, so there we go. So now this time, let's use the same process and find what we're getting here. So again, using the idea of multiplying the height times the width, which is always f of x times the width delta x. In this case, what is the height of our first rectangle? It's not f of 1/4, but actually f of 0 times still the same delta x, right? The width of each rectangle is still going to be 1/4, right? And so actually, you know what? Just to make my life easier, let's just go ahead and write that 1/4 on the outside now. So I'm just going to, I know it's always going to have 1/4 in there, so let's just factor those out. So this is f of 0 plus f of 1/4, f of 1/2, and then f of 3/4. Okay, which again, approximately 1/4. Now we know those values. That's going to be 1 plus 1.125 plus 1.5 plus 2.125. So area is approximately 1.4375 units squared. So we're a bit off, right, in terms of our estimate, right? One is not necessarily better than the other, or is it? But we have another estimate for the area underneath this curve, this one being an underestimate. Right? So then it begs this question. So far we've figured out two different ways of coming up with an estimate for the area underneath this curve of this function using geometric shapes that we do know the formulas for. So then the question could be, well, how could I improve my estimate here? What could I do to improve my estimate? Think about that for a second. And for a lot of students, the answer is to, maybe we can just take the average of the two. And that would intuitively make sense. But it's important to note that this area here, for example, for this particular rectangle, is not equivalent to exactly equal to this area here. So those differences are not exactly the same. So although it'll get you a better estimate, it won't be exact. How can we make this estimate exact? And the answer lies in the number of rectangles we use here. We took this region and we divided simply using 4 rectangles. That's not a huge number. But think about what would happen if I were to use 10 rectangles, or 100, or 1,000, or 1,000,000. Let me just demonstrate that idea. So if I'm going to just see if this works. And, okay. Oh, it went away. So here, let me actually, in fact, just go ahead and zoom in on this. And right now we're looking at some Riemann sums that are both negative and positive. We haven't discussed that yet, so don't worry too much, but I just want to hopefully model this idea. Right now, from 0 to 3, or from -1 to 3, we're only using 5 rectangles. You actually can't see that other one, so let me just go there. What if I were to increase the number of rectangles from 5 to... Oh, what happened here? Let me go ahead and reload that one. I'm not exactly sure what happened. All right, so I'm not going to fool around with it too much. Let's just see what happens when we increase the number of rectangles. And I'm going to do this kind of slowly. Ask yourself, how much white space now do I have? Let me actually even zoom in on that, see if that messes it up too much. So if we started out with just 4 rectangles, look at how much white space, look at how much we're off by. Now look at what happens at that white space as I increase the number of those rectangles. I mean, if I go up to 84, 85, I mean, that's really, really good. I'm at 100 right now. How much better do you think my estimate would be if n approached infinity? What have we talked about so far, all of this chapter, about what concept do we have in this chapter that discusses what happens to something as n approaches infinity? Yes, the idea of a limit is what we're applying here. We can use and leverage the power of limits to actually look at what would happen to our area, what would happen to our summation, because this is what we have here is a summation, right? We're looking at the sum of something. What happens here as we take the limit of this summation as n approaches infinity? Right now, n was just 4. We only added up the sum of 4 things, 4 rectangle areas. What happens as n approaches infinity? So that idea of using a limit is really what the basis is for finding the area underneath a curve.